Hi everybody, let me introduce you to this very simple game that I call Duhdhohnium 1.0. The name comes after the Italian word dado, that means die in English. Its plural form is dadi, that is dice in English. Actually, in this game we will use dice. This is a classical 6-face die, but we will use also 8-face die, 10-face die, 12-face die, as well as a 4-face die and 20-face die. What's the aim of the game? What are the learning objectives? Essentially, getting acquainted with data analysis to investigate the structure of matter. What's the underlying idea? In physics, in science, when we study a system, what do we do in order to study its characteristics? We perturbate it. We use a perturbation. The perturbation hits the system, and the system emits a signal. The signal is detected by the observer in order to study the system. Now, we have a system, as we have in real science. We have a system, but this system is essentially a set of dice. Our system is made up of a certain number of dice. We do not know how many dice, we do not know how many faces each die has. How can we know these properties? How can we know these characteristics of the system? We perturbate the system. And how can we do this? We simply throw the dice. This is our perturbation. But we must imagine that we do not know what dice we have in our hand. So we throw the dice, the set of dice is perturbated, and consequently it emits a signal. What's the signal? The signal is simply the outcomes, meaning the numbers that are printed on the top of the faces of each die. When you throw a die, you read a number on the top of the die. These are the outcomes, and each die has its own outcome. So our set of dice is made up of a different number of dice. We consider the sum of the outcomes. We do not consider each single outcome in order to make the game more interesting. So we consider just an integrated signal. That is the sum of the outcomes. We have just a single number. And finally, the observer is just us, as always. So, what's the aim of the game as regards the game strategy? We have to guess the dice, essentially. Guess the dice is our task. What dice make up the system? This is the question that we have to answer. So, first of all, we have to determine how many dice make up the system and how many faces each die has. These are the two questions that must be answered in this very simple game. We have to determine the composition of a set of dice. Determining the composition means to know how many dice and how many faces each die has in order to understand what kind of die make up the system. Number of dice and type of dice. How can we do this? How can we answer this question? We will see it in the second slide. For example, let's suppose that we are working with a 6-face die. These are the outcomes. First of all, we have to work out the partial sum, meaning that if you have number 2 as the first outcome, the partial sum is obviously just 2. Then, if you have 2 and 6, the partial sum is 2 and 6, that is 8. And then we sum the third outcome, 12. And again we sum 16, and once more 17, and so on. And so we work out all these partial sums. the sum of the first two, the sum of the first three outcomes, and so on. Now we work out the average. The partial average, this is 2, this is 4, this is 4, this is once again 4, this is 3.4, and so on. What are we going to obtain? The expected average should be 3.5. That is simply the sum of the 6 different possible outcomes, because they are equally probable. They are equally likely to be obtained. So the expected average is just the sum of the possible outcomes divided by the number of outcomes. For a 6-face die, this expected average is just 3.5. If we should have 600,000 throws, we should expect that they would be equally distributed between number 1, number 2, number 3, 4, 5, 6. So the average wouldn't change, and we would obtain 3.5 once again. If the number of faces changes, the expected average changes. So for a 4-face die, we should obtain 2.5. For a 6-face die, we obtain 3.5, and so on. If we consider a set of dies, so for example, if we take a 6-face die and a 20-face die, the expected average will change. It will be simply the sum of the expected averages of the two different dies. 3.5 for the 6 faces and 10.5 for the 20 faces. And if we have a set of 3 different dies, 4, 8, and 12 faces, the expected average is simply, once again, the sum of the expected averages of the single die. So according to the number of dice and to the different kind of dice, we will obtain a different partial average, or saying it better, the partial average will converge to a different number. For example, here the expected average is 3.5, so after some throws we expect to obtain something that converges to 3.5. If we have, for example, a 20-face die, it should converge to 10.5 for a 20-face die. So the plot of the partial average allows us to understand what kind of die we are considering. We have another weapon, another tool to understand what dice we are dealing with. And this is the frequency distribution, because each combination of dice has its own frequency distribution. If we consider a 6-face die, all faces are equally likely to be obtained, to be observed. So the frequency distribution will look like this. All outcomes are equally probable. The histogram will look like this. If we consider 2 6-face dice and we take their sum as our signal, the histogram will look very different. You can work out by your own, however, the histogram will look something like this. So let's say the frequency distribution that we could call half in jest, half in earnest spectral distribution will look different according to the set of dice. So we have, in conclusion, 2 different tools to understand what are the dice that make up our system. We have a plot of the partial average, and according to the number, according to the value to which this partial average will converge, we will know what dice we are dealing with. We can also use the frequency distribution in order to get rid of any doubt and be sure of what is the composition of dice, what is the combination of dice that make up our system. Using these two plots, we can guess what dice make up our system. Now, let's see how Duhdhohnium has been implemented. First of all, it runs on an Excel worksheet made up by 4 sheets named Theoretical, Measurements, Both, and Instructions. Let's start with the Measurements sheet. In column B, the yellow one, the outcomes are to be written one after another. For example, let's suppose that we are rolling a 6-face die. These might be the outcomes of the first throws. For example, 4, 2, 6, 5, 1, 3, 4, 2, 5, 6. When we have a number of measurements that we consider large enough, we press the Ctrl and M keys in order to run a macro. The macro is called measurements, and suddenly some statistics appear on the sheet. The first column is used simply to count the number of measurements, 1, 2, 3, and so on. In column C, the partial sums are worked out. So 4 and 2 makes 6. 4, 2, 6 is 12. 4, 2, 6, 5 makes 17, and so on. In column D, the partial averages are worked out. So the average, when we have a single measurement, the average of 4 is just 4. 2 and 4 makes 6. 6 divided by 2 is 3, and so on. Columns A and D are copied and pasted in column J and K in order to plot the upper graph, the scatter plot. Columns M, N, and O are used for the lower graph, the histogram. In column M, this one, the observed outcomes are reported. Column N works out the absolute frequency for each outcome. And finally, column O works out the relative frequency for each outcome. Now, suppose that you have an educated guess as for the composition of the set of dice that we are rolling. To check whether your guess is correct or not, there is another macro called Theoretical. You can run this macro by pressing Ctrl and T. The macro asks you the number of dice that, according to your hypothesis, make up the system. Let's suppose 2 dice. Then the macro asks you the number of faces for each die. Let's suppose, for example, a 4-face die and a 6-face die. The macro output is the following. It writes in the first columns, the number of columns depends on the number of dice, all the possible outcomes for each die. These are the outcomes for the 4-face die, and these are the outcomes for the 6-face die. In column J, all the possible sums of the outcomes are worked out. In columns M, N, and O, as seen in the measurements sheet, the absolute and relative frequencies for each possible sum of outcomes are given. Using columns M and O, the histogram of the relative frequencies can be plotted. To compare the experimental outcomes with the theoretical ones, the macro both can be called pressing Ctrl and B. This macro copies and pastes the 2 histograms and the 2 relative frequency distributions, meaning both the experimental and the theoretical ones. By comparing the histograms and the frequency distributions, the hypothesis about the composition of the set of dice can be checked. Now, let's see an example of how this game actually works. Let's suppose that someone, not us, is rolling a bunch of dice. We can't see the dice. We neither know how many dice make the system, nor how many faces each die has. We are simply given a single number that is the sum of the outcomes of all dice. We write this number on the yellow column. In our example, we use 50 measurements just to make things more clear. Then, when we think we have a large enough number of throws, we press Ctrl and M to have the statistics. After running the macro, we see that the partial average converges to about 7.5. However, we know that this plot might not be very precise since we do not have an infinite number of measurements. Let's see some possible scenarios. First of all, we see that according to the number of dice that make up the system, the lowest possible sum of outcomes changes. When we have a single die, the lowest outcome is just 1. When we have 2 dice, the lowest possible sum of outcomes is the sum of the lowest outcomes of each die, that is, 1 for die number 1 and 1 for die number 2. 1 and 1 is 2. This is the lowest possible sum of the outcomes for a 2-dice system. Consequently, for a system made up of 3 dice, the lowest possible sum of the outcomes is 3. 1 for die number 1, 1 for die number 2, and 1 for die number 3. 1 and 1 and 1 is 3. We see from our data that we have never observed an outcome equal to 1, so we are extremely unlikely to deal with a single die. Moreover, since we have actually observed a sum of outcomes equal to 2, we must rule out the hypothesis of a system made up of 3 dice. No 3-dice system could ever score a total outcome equal to 2. Keeping this in mind, let's see the possible combination of dice that can represent our system. A 14-face die might have been the answer, since the average of an infinite number of throws of a 14-face die is 7.5. Unfortunately, it is fairly unlikely to have a system made up of just 1 die, since we have never observed an outcome equal to 1. However, we can't completely rule out this option. Taking into consideration a 2-dice system, either an 8-face die plus a 4-face die or 2 6-face dice might be the correct answer, since both systems converge to a partial average equal to 7. Even a system made up by 3 4-face dice converges to 7.5. However, we said before that a 3-dice system must be excluded. Therefore, we are going to check 3 possible options: a single 14-face die, an 8-face die plus a 4-face die, and 2 6-face dice. Let's see what the frequency distribution tells us about these hypotheses. Let's run the theoretical macro for the 14-face die system. Control T. How many dice? Just 1. How many faces? 14. And this is the output. Control B. We see that the 2 frequency distributions are extremely different, so we can exclude such guess. Let's check now what happens with a 2 6-face dice system. Control T. How many dice? 2. How many faces? 6. How many faces? 6. This is the output. Control B. We see that, again, this is not the case. The distributions are very different. Let's try now the 8 plus 4 system. Control T. How many dice? 2. 8 and 4, and then Control B. These 2 distributions are fairly similar, especially as regards the highest values, which are very close to each other. 0.14, 0.125. So these values are very similar. Consequently, we can infer that the 8 plus 4 system is the most probable system. And this is actually the system that was used in this simulation. We used 2 dice, an 8-face die plus a 4-face die. And so this is it. The presentation of the Duhdhohnium has ended, and I hope you will have fun with this simple game. Bye to everybody.